Today, we are staging a search showdown. We're going to look under the hood to see how our devices find that one specific contact or photo in a sea of data. It's a real battle of algorithms, so let's dive right in.
You know, it really feels like magic, right? You type a name and boom, the number's right there. You search for some product online and it just appears. Well, that's not magic. It's the result of some seriously powerful search algorithms. And today we're going to pull back the curtain and see exactly how they work.
And to make all this feel real, we're going to build our own little program from scratch, the Atom Finder. It's a simple Python program that's designed to do just two things: store and find the names of atoms. It is the perfect little laboratory for our search challenge.
Now, to build our Atom Finder, we're not just going to write one giant, messy block of code. That gets confusing fast. Instead, we're going to organize it into these neat, manageable, and reusable pieces. And that brings us to our first really big idea: procedures.
So what is a procedure? Well, think of it like a mini program living inside your main program. You just give a set of instructions a name, and then you can run all of those instructions just by calling that name. It's a fundamental way we're going to keep our Atom Finder code clean and really efficient.
And here you can see exactly what I mean. On the left, we define the procedure add atom. That's kind of like writing down the recipe for adding an atom. Then over on the right, when the user chooses A, we just call that recipe by its name. See? We don't have to rewrite the instructions every single time. We just say, hey, use that add atom recipe right now.
So why even bother with this? Well, the benefits are huge. First, your code becomes way shorter and much easier to read. You can also reuse the same procedure again and again, which saves a ton of time. And it's fantastic for teamwork. I mean, one person can be writing the add_atom procedure while somebody else writes the search procedure. This whole idea is called modular programming, and it's how basically all serious software gets built.
All right, so our program is nice and organized. Now let's get to the main event. How do we actually find an atom in our list? We'll start with the most intuitive, straightforward method there is: the linear search.
The name really says it all here. A linear search is kind of like looking for a specific book on a very long shelf by starting at the very first book and checking every single one in order until you find the one you're looking for. It's simple and it's super direct.
The process here is dead simple. You start at the beginning of the list. Is this my atom? Nope. Okay, move to the next one. Is this my atom? Still no. And you just keep going down the line until you either find it or you run out of atoms to check.
You know, for our little Atom Finder program, this method works just fine. But what happens when you try to scale this up? What if you're a website searching through millions of products? Checking every single one would take forever. The beautiful simplicity of linear search is also its greatest weakness. It can be incredibly, incredibly slow.
Okay, so if linear search is the brute force method, what's the more elegant, clever solution? Well, that brings us to our next contender in the showdown, the binary search.
Now, before we even get into how binary search works, you need to know its one big, non-negotiable rule. The golden rule, okay? The list of items must be sorted in order, say alphabetically. If it's not sorted, binary search just completely falls apart. It will not work.
So here's the core strategy. Instead of starting at the beginning, you jump straight to the middle of your sorted list. You look at that middle item and you just ask one simple question. Is the atom I'm looking for alphabetically before this one or after this one? I mean, think about the power of that for a second. With just one comparison, you've instantly eliminated half of the entire list. Gone. Then you just do it again. You take the half that's left, jump to its midpoint, and eliminate another half. You just keep dividing and conquering until you zero right in on your target.
So we have our two contenders: linear search, the simple, steady plotter, and binary search, the speedy, clever strategist. It's time to put them head to head and see just how different they really are.
And this table just breaks it down perfectly. Linear search is simple, right? And it doesn't care if the list is sorted or not, which is a huge plus. But its big disadvantage? Man, it can be painfully slow with big lists. Binary search, on the other hand, is lightning fast. But, and this is a big but, its big catch is that you absolutely have to sort that list first, and that takes time and effort.
Let's put some real numbers to this to see the impact. Imagine our list has 128 atoms. If we get really unlucky and the atom we're looking for is the very last one, a linear search would have to make 128 checks.
Okay, now for that exact same list of 128 items, how many steps does binary search take in the absolute worst case scenario? 7. Not 128, 7. It just splits the list in half 7 times to find any item it's looking for. The difference is just staggering.
And this visual really drives the point home. Look at the red bars for linear search. As the list gets bigger, the number of steps it has to take just shoots straight up. Now look at the orange bars for binary search. They barely even move. That massive performance gap just gets wider and wider as the data gets bigger.
But let's not forget the catch. As our source material really emphasizes here, the incredible speed of binary search comes at a price. Sorting a list, especially a huge one that's always changing, can be a really time-consuming job all by itself. That's the trade-off you always have to think about.
So we've seen the simple method, we've seen the smart method, we've looked at the raw numbers. So what's the final lesson from our little search showdown?
Well, when it comes down to it, there's no single best algorithm. It's all about picking the right tool for the right job. For a small, messy, unsorted list, the simplicity and flexibility of a linear search is actually perfect. But for a massive, organized library of data that you have to search constantly, well, the upfront complexity and effort of sorting for a binary search pays for itself 1,000,000 times over in pure speed.
And that leaves us with a final thought to chew on. Knowing just how unbelievably fast binary search is, why would a professional programmer ever deliberately choose the slower option? As we've seen today, it's all about context and trade-offs. Because sometimes the simple solution really is the smartest one.